Hey, all right, welcome again. I got another video solution here coming. There has been a few questions. It's mostly really a math question about chapter 23, problem number 29. There's a pretty hard integral in there to do, and everybody in the Zoom session today was asking me really about the math and not so much really about the physics. But there's two really neat things I think I should say about this problem, and I debated and decided, well, I'll just do a full solution. And so let me go ahead and do a full solution, and particularly focus your attention on the math part of it. But if you're familiar with the problem already, there is a charged rod like this, okay? And up here on the y-axis and at the perpendicular bisector, and that's important. It even reads here, a thin rod of length L. So the rod is of length L and has a uniform charge density of lambda. And so lambda is the charge per length. So that means we could think of lambda as the whole charge divided by the whole length, or we could think of it as a little bit of charge on a little bit of length. So we'll take advantage of whichever one we need, and maybe even need both. Okay, lies along the x-axis as shown, and then A says show that the electric field at point P, a distance y. So we'll say this up here is a distance y. From the rod along its perpendicular bisector has no x component and is, let me pause right there, no perpendicular bisector component. This is, I wanted again to take this moment. I had just finished doing the video solution to number 60. And I like number 60, I'll even bring it back into this picture here, because I took what looked like a hard problem with 8 charges and through a lot of physics and symmetry reduced it down to a single calculation. And that skill is something that you'll begin to develop, and it is something that is crucial for this. You won't have enough time to do all the homework, let alone do the test, if you don't see some of the physics and some of the symmetry that's going on. And so in this case, if I were to take a small piece of the rod here, maybe this little piece right there, but what I like to call its symmetric twin over here, and you look at the electric field that is created by just those two pieces, so not necessarily yet the whole rod, but just those two little pieces, the electric field from this little piece would be something like that, and the electric field from this little piece would be something like that. And so if these little pieces are the same size and they're symmetric, meaning they're the same distance away, that means they have the same charge and they're the same distance away from that point. So both of them will make the same electric field. They will be at the same angle. Maybe I'll make this a little longer so it looks like it's the same length. And that means when you look at the components here, the x component, the horizontal component, would cancel off. And you can do that all the way through. So these two give you 0. Another symmetric set of points, what I call the symmetric twins, these two would do the same thing. Now their angle would be a little lower, and their strength a little less because they're a little further away. But again, when you look at those symmetric pairs there, the x component cancels off. And so right away, without really much math work, all just kind of understanding the conceptual idea of the electric field, I could say that the field in the x direction is 0. And there's only going to be a field in the y direction. And that was the first part of question A, which I'll read it again. It's to show that the electric field at point P, a distance y from the rod, has a perpendicular bisector, has no x component. Yeah. So there it is. I've done it. No x component. And is given by, and then they give a little equation. So that must be the y component. Okay. So let's continue on with this problem. So the electric field, and I'll just say in the y direction, but that's also the total electric field, since we just said there isn't going to be an x component, would be the sum of the electric fields in the y direction. And so I'll write this in the beautiful calculus form. And so remember where this came from in your calculus class. This is the sum of small little pieces of something, in this case dy, and you're going to add them up an infinite number of terms. That's why Newton, used the this symbol here. I don't know if you know the history behind that, but he was looking at it as a summation, and so he kept writing s, but he wanted to distinguish it from an s, and so he started elongating it. And so this is our symbol then for the integral. It's an s. It's a summation. Well, that helps me. I'm also told, never been overseas, but told that if you visit his house in England somewhere, that this symbol is all over the outside exterior wall of Newton's house. Okay, well, let me continue here. Because then I would say this, that technically I'm adding up the whole rod. And so if we let the x-axis be right in the center of this rod, then we would be starting our summation at a negative L over 2 for the position of that first chunk. And then get another chunk and another chunk and another chunk and another chunk. And you would add it all up until you get to L over 2. Okay. But, as we argued before here, the vertical components of the symmetric twins are the same. So why don't I do this? Why don't I just add up from 0 to L over 2? And so here's 0 to L over 2, and double it. And so I'll put a 2 out in front, and then just add up all the vertical components. So that too might make it a little bit easier. Your call on that. But usually integrals that go 0 to something are a little bit easier, but it's just twice that. You just have to justify it. So the same way we justified that the x component goes to 0 is the same way I'm going to justify that the y components, I just have to do half the rod and double it. Okay, so again, continuing on here and turning what could have been a pretty hard problem and still has a tough integral to do into a fairly, hopefully easy one. So here's 0 to L over 2. And of course, to get the y component of this, let me kind of make a little line here. Let me just think about this little chunk. This little chunk would be then Coulomb's constant times that little chunk of charge. I'm going to call that a dq. Okay. And its distance away squared would be this distance. But if I use Pythagorean's theorem, this is at some position x that's changing as I go to each little chunk along the rod. So I will represent that as just an x squared. And then this doesn't change, so this is a y squared. And so that is the magnitude of it. Now remember, we don't just want the magnitude. In fact, maybe I should have wrote here, this would be the magnitude times, and if I call, say, this here theta, to get the vertical component, I would want cosine theta. So maybe I'll throw that in there now here. Okay, so there's the magnitude, and then there's cosine theta. Okay, well, continuing here. Here's the 2. Here's my integral, 0 to L over 2. And I've got the Coulomb's constant. Now right here, let me jump back to here. This would be lambda dx as I move that over. And as I look a little closer at cosine, And look at this and here. Cosine would be this adjacent over this hypotenuse. So the adjacent is y, and the hypotenuse is the x squared plus the y squared to the 1/2 power. So if I put that into here, there's the y. And these two are the same, so let me write that as an x squared plus a y squared to the 3/2 power. Yay! Okay, so there's my integral. And I didn't get any questions today about all of this. I did want to start the problem at the beginning because I told you there were two things I wanted you to really see. And one is this symmetric argument and using a lot of physics in order to simplify the math. And so that's why I only have to do half of it, and that's why I did this step. And I'm hoping that this isn't too hard for you after you've done some challenging ones on this. And certainly nobody asked about this. What I did get questions on was kind of this next step. And so this next step, if you take the constants out in front of the integral. And so now remember, y is a constant. Sometimes that's hard to see. But y would be a constant for this problem because as we're adding up the little chunks, their position on the x-axis changes, but not this vertical piece. So again, that might be a little hard to see. But we end up with an integral that is not a simple integral. It's one that you did see in your Math 160 class. It's a harder one than I've shown you so far on the video solutions. But this is why I wanted to pause here. I wanted to say that this one does not look like a u-sub like some of the harder ones we did. Remember, to be a u-sub, you have to have the derivative, so you'd have to have an x up here. Then it would be a perfect u-sub. And that's the one I showed you in an earlier video solution. And so I would expect you to know how to do that. This one, I don't know if you remember from your trig class, without that, and this raised to a 3/2 power screams trig sub. And it might have been a while since you've done that, but this is a trig sub one. So I'm going to give you two ways to solve this. One way is just go to Appendix B. Let me look at the Survey PDF and go to Appendix B. And I want to point out Appendix B here because there's something neat here that Appendix B has a lot of math reviews. And so if you find yourself struggling with maybe some of those trig identifications or maybe some geometry or maybe some of the rules of exponentials, all of that is reviewed for you in Appendix B. Of course, in today's information age and you're all at home, you can also Google it here. But I say that because in Appendix B, and it would be in the PDF on page 1,400 and looks like 47. There is a whole table. It's table B5, and it's got a long list of these integrals. And some of them are easy, you should know, and some of them can be quickly solved with a u-sub, so that's what I would expect. But this one takes a trig sub. So I would say, and this is what the author wants you to do, really, is don't work this one out per se. Look it up, okay? And the same thing could be said on the test. The tests are going to be open book, and so just look at that, okay? You don't need to spend a lot of time on it. Now, it's probably good, so I want to show you, actually, because I did have two people ask in the Zoom section if I could review the math, and we never got back to it. I said, well, yeah, let me do that, but let me stay focused on physics questions. And then we never got back to it. So I thought I'll just make a quick video of the whole solution and including that. So those were the two big pieces, the physics of the symmetry here, and also showing you math review, if you will, of a trig sub, if it has been a while. But the easier way to do this problem, and the intent of the author in doing this problem, was really just to go to the Appendix B, scan the table of integrals, and they've got all kinds of trig functions. One, like I'm looking at it now, I see like the integral of cotangent. It's not simple. You know, the integral of cotangent x is the natural log of the sine of x. Wow. That's a heck of a incredible integral. Or wow, look at this one. What is the integral of the secant function? It is the natural log of the tangent of x over 2 plus pi over 4. So to ask you to do that is really more of a math question, and so I don't want you to spend too much of your valuable time. It may be nice to know those, but that's why we make these tables. Those would take hours to do, perhaps. Now this one wouldn't. This is just a trig sub, and so trig sub is like one step above a U sub. So I'm trying to say is you're kind of expected to know up to things like a U sub, but some of the real harder ones, no. Partial sums, for example, no. And these trig ones, yeah, no. All right, so with that in mind, let me just get a whole new sheet here. And for anybody interested, you can keep watching the video and see what the solution is here. So let me just write here at the top of the page the integral of dx over x squared plus y squared to the 3/2 power. And it's probably worth maybe coming back to the picture I had here, because you can see the value of the trig sub when you look at a right angle triangle, knowing this is the x and this is the y. And so if we call this theta, you can see then that the tangent of theta is x over y, which means y times the tangent of theta is equal to x. And what I was trying to say here is the trig subs come out to be nice when you switch all these variables to the theta. So in the denominator here, let me replace x with y squared tangent squared theta plus y squared to the 3/2 power. And in the numerator, up here, let me take the differential of this. So the differential of x is dx. And the differential of this side, as long as y remains constant, which again, I'll go back to our problem for a constant, the value of y. This angle would change. And the derivative of a tangent is a secant squared d theta. So that's the differential. In fact, I'll use this as an opportunity again. If you don't remember the derivative of a tangent, go to Appendix B, because there's another table, and it probably is the one before 5, so I'm going to guess 4, that lists all these derivatives. In fact, maybe I'll just confirm that. What's my page up there? Yeah. And page up. Yeah, it is table 4. Okay. So what I can do now is put that into here. So this becomes y. This becomes secant squared theta d theta. Okay. So that's our change of variables. That's our trig sub. We changed it from an integral on a Cartesian coordinates to a polar integration. And then luckily this simplifies quite a bit. Let's see here. First of all, maybe you could see that both of these have a y squared in them. So if we factor that out, then we would have this y squared, and it would be raised to this 3/2 power. And we would be left with a tangent squared plus 1 to the 3/2 power. And maybe I'll just leave secant squared alone for a moment. This simplifies, of course, the square and the square root cancel. That's a cube with that. Makes a 1 over y squared. And again, maybe I'll leave the secant squared alone for just a second. And then this one hopefully is screaming at you one of those trig identities. It's one of those Pythagorean trig identities. And again, this is my chance to talk about Appendix B again. I'll go up a couple pages because these trig identities, these are the double angle ones. Where's the Pythagorean ones? Ah, here they are. I don't know if he writes them all out there. And it's not in a table. Looks like it's just a little list there. All right, but they're in there. Maybe I'll just remind you that cosine squared plus sine squared equals 1. That's probably the easiest of the Pythagorean trig identities, because if you divide everything by cosine squared theta, this first term is 1. Sine over cosine is tangent squared, and you get 1 over cosine squared, which we could write as a secant squared. So this really is secant squared raised to the 3/2 power. Now you see the beauty in this. Because this bottom one, secant squared and the square root, then just makes a secant cubed. And so the top two cancel off, and you're left at the end of all of this with just one secant. And since secant is 1 over cosine, we can flip that and get a cosine theta. Yay! And then we have a really easy integral to do. And so what started off looking like a hard integral to do, or back here, after doing the trig sub, we got a very easy integral because the integral of cosine is just sine. Oops, no integral. Now I'll also say I kind of dropped the limits, so I'll just put a little from here to here, because I don't think there's any point in writing the limits of theta, because I really wanted the limits back for x. So remember, this was 0 to L over 2. So I'll come back to that in just a minute here. But I think the best way to finish this problem is not with a theta, because we don't want the theta. That's just a variable that we threw in. There's no theta in here, right? This is what we want. So let me put in sine theta. And so coming back up to this diagram, sine theta would be the opposite x. So here's sine opposite x over this hypotenuse, which would be x squared plus y squared to the 1/2 power. And now we could say evaluated from 0 to L over 2. So taking that back to our problem, we have two options. We could either A, just go look this up in table 8b, or we can do this trig sub. And like I said, since a few of you asked, I thought I'd put it in video there. And so here I have the 2 Coulomb's constant lambda y. And then now I've got this integral, which would be 1 over y squared x over x squared plus y squared to the 1/2. Again, then evaluated from 0 to L over 2. And so maybe I'll first just cancel off one of the y's and get a 2. Coulomb's constants, lambda, constant lambda over y. And then now when I put this in, let's see, I got the y. This would be an L over 2 here. This would be an L squared over 4 when we square the x plus a y squared to the 1/2 minus a 0. So I guess we don't need that. And we could even cancel that. And I guess, good, I did it. Though I thought there was something else they asked about this one. Let me come back to the question now that I jumped over and did here. Due to the oh, actually, I could have left it as sine. They left it as sine theta. Okay, is given by, and then they say sine theta. Okay, all right. So maybe I should have left it as a sine of a naught, because they call the full angle theta naught. Well, anyways, I think that part you guys got. Just wanted to show you this integration with the trig subs as well as the symmetry. All right, bye now.